Well, the next speaker is going to talk in English. Then his name is Daniel Herranz. He's a professor from the Chemical, Physical Applied Department, and I prefer he just say the title of the talk.
Hello everyone, good afternoon, and thanks Pilar for the introduction. So this talk is going to be about the very short state of the art of ion exchange membranes for inorganic redox flow batteries. So we are going to see a brief introduction of what are redox flow batteries, the role of the ion exchange membranes in these devices, and also some of the recent advancements in membranes for this technology. So well, first of all, what are the redox flow batteries? We need to understand what are we talking about. So a definition that we can find is that redox flow batteries are electrochemical devices that convert reversibly electrical energy into chemical energy, and they store it in active redox species that are in external tanks. So as you can see, a typical configuration of a redox flow battery would be like this. We have the cell in the middle, which is where the reaction, redox reaction conversion takes place. And then we have the external tanks, which, as we are going to see, they are very important because it makes completely the difference with other technologies. So if we compare with other technologies like the conventional batteries, for example, the lithium batteries that we are very used to, we have several advantages considering the redox flow batteries. One of them is the possibility to reach very high capacity, and this is linked with the second one, which is the decoupling between the capacity and the power of these devices. What does it mean? The capacity is dependent of the total amount of redox species that we have, but as we saw, they are in the electrolyte, so they are dissolved, and they can be stored in external tanks. So we can have very large external tanks, and then we can store a lot of energy. And then the power of these devices only depends on the active area that we have for the electrochemical conversion. So we can play with that as we want. We can have very small cells for the power that we need, and we can have huge tanks to store a lot of energy. So for example, this works very well with renewable energies. So we can produce a lot of electricity with the renewables. Then we can store it in these very big tanks, and then we can use it when it's needed. And as I said, this is a main difference with other batteries, like for example, the lithium-ion batteries. We have the solid electrolyte, so they are both coupled, the capacity and the power. Because if you want a lot of capacity, you need a very big electrode, and then you will have a lot of capacity, a lot of power, but you cannot decouple both things. Another advantage that they have is the long duration and for storage and lifespan that this technology can address. And well, the main disadvantage is the low energy density, because as we said, typically the redox active species are dissolved in the electrolyte, and we cannot dissolve as much as we want. There's some limitation, so the energy density is lower than if we have a solid electrodes. So well, we have different types of redox flow batteries. For example, they can be classified according to the electrolyte system and the aggregate state that we have. Well, it's not very clear, sorry, but here we have protic electrolytes. The most typical one is in aqueous systems. And also we have a protic conventional molecular solvents, and also there are some people using ionic liquids or even other possibilities. And then we can divide them by the aggregate phases that we have. We can have the one phase, for example, the all liquid. So both sides are with the active species in the liquid state because they are dissolved. Or we can have other options like the two phases, which are called hybrid fuel cells, and sometimes they are called not true fuel cells because when one of the electrodes we have that the electrochemical species are deposited in a solid state electrode, we are losing one of the main advantages that we cannot store that in an external tank. It's just limited by the electrode. Here we have a few examples of the inorganic redox couples used in these redox flow batteries. So as you can see, there are plenty of them. Then you could see the letters, they mean like how much is the technology development, because there are some of them that are just they are starting to be investigated. And there are a few that are being commercialized, but just a few nowadays. And the one that it's the most famous one, the best known, and it's being implemented commercially nowadays, is the vanadium redox flow battery, which has vanadium in both sides, in the anode and in the cathode, in both cells. So I'm just going to explain a bit, because this is really the most relevant one nowadays. So what we have is that this is a picture of what a vanadium redox flow battery would look like. And we have in the negative electrode that the vanadium 3 plus converts to vanadium 2 plus. This is in the charging process. And in the positive electrode, during the charging, we have the conversion of the vanadium oxide ion, which in this case is in the 4 plus state, to the vanadium dioxide ion, which in this case in the 5 plus state. So here we are playing with the 4 oxidation states of the vanadium metal. And as you can see, well, it has very beautiful colors. So it's also a nice thing to work with this kind of batteries. So the total voltage that we have is 1.25 volts, the standard potential of this reaction, and it allows to store quite a good amount of energy in the material. And so the maximum energy density that it's obtained nowadays with this kind of batteries, it's around the 30 watt-hour per liter, which is quite good. It's quite okay already, but it's not still as high as the lithium batteries, for example, which are approximately an order of magnitude higher. But this is because of what we said, the difference between the liquid electrolyte and with the specific salt, or the positive electrode or negative electrode with the condensed species in the other batteries. And what's very relevant is that these the membranes that are used to separate both chambers, because what we have here is all this process working in one side, in one of the chambers, and the other one in the other side, is that this has to be separated to avoid the mixing of the species. And the membranes that are usually used nowadays, they account for approximately like 30–40% of the final cost of the stack. So as you can see, this is a really important drawback. And that's the main reason that a lot of research is being performed to try to enhance the membranes and reduce the costs, of course. So as we said, we need to separate both chambers, and the vision that we do needs to have some specific requirements. So the membrane, the separator that we are going to use, need to be impermeable for the reactive species. So we want to avoid the crossover and the mixing of the reactive species, but it has to be permeable for the supporting ions, because otherwise we couldn't balance the charges and it couldn't work. So we need both things at the same time, which is one of course of the main points of these separators. And then of course it has to be isolator for the electrons to avoid the shortcut of the electrical circuit. And in order to obtain this, there are different strategies. We have, for example, some devices that are being investigated that they have no membrane, or they are the membraneless redox flow battery. And in this case, they are based on immiscible electrolytes. So since they don't mix, you don't need a membrane, but still they're in a very early stage. But this is an interesting and a different approach. Then we have the porous separators. And these are based in the size exclusion effect or sieving effect. This means that because we have this separator in the middle, depending of how big, how large the pores and the channels are in the separator, they may or not may allow the conduction of some of the ions. So they have to be these pores have to be small enough to prevent the crossover of the active species, but large enough to allow the crossover of the supporting ions. These are being quite used and they are continuing to be used nowadays and under research, but usually they are not still good enough because the crossover of the active species is still too high. So usually they're being investigated, they are trying to reduce it and to improve the structure of these pore separators. But the ones that are being more used commonly in redox flow batteries are the ion exchange membranes. And what we have in this case is that we have fixed charges that are with the functional groups that are linked, they are fixed in the membrane structure. Usually, also when we have ion exchange membranes, of course, we have some channels in the structure. So more or less always we have a mixture of ion exchange membrane with some sieving effect separation. So we cannot disconnect these both things, but the pore separators are only based in this size exclusion effect, while the ion exchange membranes have the fixed charges. Well, this is the ones that we're going to focus on. So just to have an overview of what can we do with what types of ion exchange membranes do we have? We have the cation exchange membranes. So what we have in this case is that we have, well, it's very small, but you can trust me that what we have is that negative fixed charges in the membrane structure. So these negative fixed charges help for the conduction of positive charges because they are attracted, and then they are not that much attracted, so it helps to conduct the positive ions to the membrane. The most known and typical cation exchange membrane is the nothing membrane, which structure is here. It has a hydrophobic part and an hydrophilic part with the sulfonic acid groups, and it forms this kind of channels. So they have been tested for so long, they are very good, but they are very expensive also. So most of the effort is trying to find membranes that may have similar or even better performance than the nothing membranes, but with lower cost. And also one of the things here is that the cation exchange membranes, since they help to conduct positive ions, for example, if we are working with the vanadium redox flow battery, as we saw before, the reactive species are positive ions. And we don't want to help conduction through the membrane of that. We want the active species to stay in its chambers. So one of the drawbacks that the cation exchange membranes have is that they have usually a higher crossover of the vanadium ions than other types of membranes. If we go to the anion exchange membranes, we have the opposite. We have positive charges fixed in the structure, and that helps for the conduction of negative ions. And this has also an advantage, talking about the vanadium redox flow battery, which is the dominance question effect, which is based on the electrostatic repulsion of the vanadium ions, since they have positive charge. And we also have positive charges inside of the membrane. The positive ions are repelled and they don't tend to go through the membrane. So these membranes, opposite to the previous ones, these ones usually have a better barrier to the positive ions. This is one of the reasons that they are being quite investigated for vanadium and other redox flow batteries that have positive ions. And then we have the amphoteric membranes that mainly they are a combination of the two previous ones. We have mixed positive and negative charges within the membrane structure. So they try to balance the advantages of both things. They try to balance the repulsion of the positive ions, the positive ions to don't mix the electrolytes, but also they may have a better conduction of the protons, which are positive, but they are very small, so they are not that much affected by the Dominus class impact. So, well, the main aims of for membrane research, based on all the things that we saw, are the lowering of the ionic resistance to enable operating at higher current densities, because of course the higher the conductivity, the better will be the performance. We can go to higher current densities operation. To improve the barrier properties, because as we saw, there are many ways, but still the crossover of the ions have to be improved. To stop the crossover of the ions, balancing the net electron transport to minimize the capacity imbalance, and ensuring chemical stabilities of the materials for very long times, since we wanted to store energy for, a lot of hours, days, weeks, even years. It's the idea of this technology. And all of this while trying to be cost competitive with existing membranes. So there are many strategies that are being followed in order to try to get to all these objectives. And I'm going to just have a very brief overview of a couple of them so we can have an idea. So one of them is try to do the molecular design of the polymer backbones of the membrane. Since it's known that when we have excessive swelling is when the water on the electrolyte goes into a membrane, it swells, so it takes that inside and makes a bigger dimension. And so we have enlarged charged channels, and if this effect is too much, it can provoke that we have a lower selectivity and stability. So one of the ways that have been tried is to introduce groups in the backbone of the polymer chains. And for example, in this case, they are using this in this work. They are using this elementine group. They are introducing it in the backbone because it's a very rigid group, and it helps to stiffen, to make more rigid the overall polymeric structure. So they do it in the work, and they introduce it. They find, well, again, sorry, this is small, but this is the swelling ratio. So they obtain a small swelling ratio. They are successful in that, and also a small water uptake, which is most usually linked with the swelling ratio. So it looks like this is working to reduce the excessive swelling. And when they do the cycling performance, they obtain very good results. So the results are the Coulombic efficiency and the energy efficiency, and they compare with some Nafion membranes up to 200 cycles, and they see that both the Coulombic and the energy efficiencies are better than these Nafion membranes. So they have effectively improved the barrier properties, and also for electrolytes, but also they are not losing that much conductivity, because otherwise the energy density would be lower. Another possible strategy to do this is to work with the molecular design of the side chains. So we have the backbones, and then we have some side chains pending from that backbones. And we can work in the backbones as we saw, or also there's a possibility to work in the side chains. So in this work, well, sorry, you can see the work here. I think it's below the presentation. What we do in this work is that they are with the side chains. They are trying to do the cross-linking of the polymer backbone, and using this cross-linker. But why do they try to do this cross-linking? Because the cross-linking of the polymeric chains helps to reduce the water uptake. When we are cross-linking, we are making a more entangled structure. So since it's more rigid, it will have lower swelling. And then what we saw, the problem of if the solid is too much, we have the crossover of the ions and everything. So the cross-linking is very effective for that. But usually what we have is that when we do the cross-linking, we are using some of the anion exchange groups that are present in the membrane. And because of that, we are losing part of these groups, and then we are reducing the ion exchange capacity, which is linked to the conductivity. So if we lose ion exchange capacity, we lose conductivity, and it works in a worse way. But what we do in this work is that working with the side chain, the linker that they are using, of course, it consumes part of these groups, but also has the possibility to be further react to produce another sulfonic acid groups in the side chain. So we are losing some of the groups in the main chain, but we are adding another ones. So we are getting both things. We are getting the cross-linking, and also we are compensating for the losing of the ion exchange groups that we had. So what they do with this, they did the synthesis, then they check the permeability and the ion selectivity. The permeability are the field bars and the ion selectivity are the dust bars. And what we can see is that when they have an appropriate cross-linking and then the sulfonation afterwards, they really enhance the membrane properties, reducing the permeability and increasing the ion selectivity. Then they do the cycling performance. And again, this time it only goes up to 120 cycles. But okay, it's still quite a good experiment. And they go with much better results than the Nafion membrane that they are comparing, and with the membrane without the cross-linking. So they can effectively see that this cross-linking strategy has been very effective to enhance the cycling performance of the membrane and the overall system. And then other possible strategy, this is the last that we will see, is the introduction or inclusion of polymers into the channels. It can be polymers, it can be nanoparticles. There are different possibilities, but here I'm going to talk a bit about the introduction of polymers into the channels. This is a work that has been done as part of the PhD thesis of Ivan Solmeron this last year here in our group. So I was not involved, but I think there are very nice results, and it's interesting to see what has been done. So it was done here with 4 membranes, 2 cation exchange membranes and 2 anion exchange membranes. The polypyrrole was introduced in the membrane and it was in situ polymerized. And so we fill the ionic channels with some polypyrrole structure. And for that, in order to study what's the conduction mechanism of the ions, since it's not very clear, they use a 2-phase model that it was available in literature, but it was implemented for this case, and it was also improved in order to explain the results obtained. And in this model, we have this TSP, transport structural parameter, or outcome, that helps to relate how is the conduction of the ions through the membrane. So it says how is the interconnection of the gel and the interstitial phases that we have within the membrane. When it's close to 0, it's related with a random interconnection. And when it's close to 1, it's connected with a range connection that helps to promote the conductivity of the ions. So what it was observed, it was that in the ion exchange membrane, the conductivity was increased, while in the cation exchange membrane, it was reduced. And it was in accordance with the model that was being used, validating it. Why was the reason of that? What was proposed in the work is that it's because of the interaction of in the cation exchange group, we have negative fixed charges in the channels, and then the interaction of the polypyrrole with these channels reduce the availability of the ion exchange groups, and thus we reduce the ion exchange effective groups, and then we reduce the conductivity. Anyway, with both of them, because we are filling the pores, we are also reducing somehow the pore size, and that helps to reduce the crossover of the active species. So it's a very interesting approach also for this type of membranes. So finally, just a very brief conclusions. We have had a general overview of what are the redox flow batteries and what's the membrane role within them. We saw a few examples of the strategies that are implemented to improve them. And of course, there's still a wide area of research in order to improve the membranes for this kind of devices. So I would like to acknowledge the projects that made possible the research that I saw, and also the organizers of the symposium for the invitation. And well, thank you all of you for your attention.
Thank you very much. Really nice talk. Any question?
Have one. So the results you showed at the end was using natrium membrane. Is that right?
No, not exactly. So this.
Or what is the matrix?
Well, it's in some of them in the cation, because in these last results, some of them were cation exchange membranes, so as natrium, and they have a perfluorinated structure. So it's quite similar to natrium, but it's not exactly the same. So you can have perfluorinated membranes with different structures. So the natrium one, it's a bit different from this one. And the other ones were anion exchange membranes, so it's a completely different kind of membranes.
And what is the typical pore size or pore diameter?
For these ones, for these commercial ones,
I can't.
No, much smaller. Yeah. In order to have an idea, with the natrium membrane, it's about the 4 nanometers. So these membranes, I don't remember in that range.
Thank you very much, Dan. What's your approach for this problem? Working membranes, only new batteries?
Like the approach of the group,
What you doing in this topic?
Oh, yeah. So my approach is working on the membranes, and also in the electrochemical characterization. I mean, in the cell. So preparing new membranes with some modifications, and test them in the single cell.
Polymers or polyfibrol?
This work that I saw is of the PhD thesis of Ivan, so it was with polypyrrole. What I have worked is not with inclusion of something in between channels, but I worked with anion exchange membranes, and I worked changing the functional group that is in the membrane, and also doing some cross-linking, similar to the previous one that we saw. So some of the members that I worked with, they have this cross-linking, and then you can tune some of the membrane properties with a higher or lower cross-linking. So if you have a higher cross-linking, then the structure is much denser, and it's a better barrier, but you lose part of the exchange groups.
I am not interested in the topic, but what kind of solvents are used commonly for these vanadium redox flow batteries?
For the vanadium ones, they are acid solvents, and the typical one that has been used for the commercial ones is in sulfuric acid. They may have also small parts of other acids like phosphoric acid. It's used, and maybe another ones, but usually they are in the range of the 3-4 molar sulfuric acid. The typical ones for the vanadium. For the rest of them, it depends. There are many of them which are aqueous, but
I think it's like interesting to try to avoid the use of these acid solvents in order to go to safer batteries that you mentioned with the lithium ion and so on, so the electrolytes use the organic solvent and so on, which are flammable and so. So I was thinking maybe that avoiding the use of this acid solvent would be some point.
I think that of course it's interesting because of hazards that may happen. So it has some tangent use of this kind of solving that it's very acid. But mainly, if you have a system that is very well sealed, the solvent is just inside of the system, and if you don't have leaks out of the system, there shouldn't be a major problem. And then, for example, in the vanadium redox flow battery, that's something I forgot to say, is that because we are using vanadium in both sides, it doesn't matter that much if there's a bit of crossover from one side to the other, because we are working with the same metal all the time. So, for example, in these ones, then you can reuse the electrolyte. Even after a long time, probably something else is going to crash. And then you can take out the electrolyte, make a new cell, and use again the same electrolyte. So if you are not wasting the solvents and you don't have leaks, of course, probably we can find something with less than danger, but it's not I don't think it's one of the serious problems in these devices.
I have a question. It's a general question. In your point of view, why or which is the problem of the redox battery? Because a vanadium redox battery has been investigated for a long time, and it's not really a commercial battery. Then, what did you think about this?
Well, there are already commercial batteries. So
yes, I know, but in a limited point. It's not using like a.
So one of the main drawbacks of the vanadium ones is the cost of vanadium, because it's a critical metal. Of course, well, actually it's like lithium is not that critical, but also we can have lithium for everyone have electric vehicles. So vanadium, it's not that abundant. So that's one of the main drawbacks, the cost and the availability of vanadium. That's also one of the reasons that there's a lot of research on other redox pairs, like for example, on iron and cerium, that they are much more abundant and easy to obtain, but they don't work as well as the vanadium ones.
Yeah, the question is that because I know many researchers are working in vanadium redox battery, and they still, I don't say in the same point, but in similar.
Yeah, sure.
Okay. Any more questions? Okay, thank you.